Hello, everyone. As we get ready to work through a process of uh, data mining, which this class is really focused on data mining, I think it's important for us to go through a couple of early stage kind of primers. The first one's going to be on statistics in general, and many of you probably taken statistics before, so this is probably going to be a lot of review for you, but it won't be a very long video, so it won't be too painful. The second thing we're going to look at is going to be inferential statistics, and I'll have a separate video set up for that. This statistics primer is going to give you some sort of ideas of things that you'll likely encounter when we use the application we're going to use in this class called JASP. JASP is an open source statistics package, very similar to SPSS or SAS. It allows us to do a good deal of data mining, but it's important to understand the kinds of things that you'll be seeing when you use the JASP tools. So that's what these primer videos are intended to do, and we'll go ahead and get started with this first one. So the first thing we're going to look at is mean or average. They're basically the same thing. And we're probably pretty aware of averages and means. We hear it all the time. And it's basically the average value for a certain variable. So it's not too difficult. All we basically do is add up all of the values and divide by the number of instances, and that will give us the average. The average or mean, I'll use mean, settle on mean is the term I'm going to use from here on, but the mean is often designated by a bar over the variable. We usually use x. So bar over x is basically the symbol that we most often use to refer to mean. And the formula for mean is, I'm going to go through this in a little bit more detail each time we run through one of these formulas, because they can look a little intimidating at first, but if you break them down and look at what they're doing, they're not that hard. So the formula for mean is the summation. Summation basically means add them all up, right? So we're going to take every instance of x. It could be maybe we have 100 x values, we have 1,000 x values. That could be age of high school students, or it could be scores on tests, or it could be amounts of money allocated, whatever. It's a numeric value. So we're going to add them all up, and that's what the summation sign does. And then we're going to divide that by n. N is always used to represent the number of instances. So in a case like this where we had 100 different student ages, we would sum up all of the student ages, and then we would divide that by 100 because that's the number of instances that we have. So that's mean. And like I said, it's pretty straightforward, and you're probably pretty familiar with it already. The normal distribution allows us to show two things. It allows us to see the mean of a particular variable. So again, we can look at student ages, and then we can also see the scatter. So if we have a group of 100 students, say 100 college students, that's a better example, here at Central Washington University, and we calculate the mean of the 100 students, we'll get our mean value just like we talked about above, but we're also going to get the distribution, and what we often refer to as the scatter. And that's going to be a sort of a visual display of how many are above the mean and how many are below the mean. And that tells us a lot about the data set. So here's a normal distribution, and it's what we oftentimes refer to as a bell-shaped curve. The mean is in the middle, right? So typically it's in the center, and that's going to be your mean value. And you see that there are some number of values that are above the mean and some number of values that are below the mean. The shape of the curve determines the scatter, the amount of scatter. If you have wide variation in your data set, then your bell-shaped curve is going to be broader and flatter. If you have a lot less variation in your data set, then your bell-shaped curve is going to be a lot taller and skinnier. And let's talk about variance. Okay, variance really, in a simplest term, is how much do your data points vary from the mean. So how much do each of your measurements vary from the mean? This is an important measure because it tells us something about our data set. It tells us how scattered the data points are. And why do we care about that? Because if the data points are widely scattered, then the mean is going to have a bit of a different meaning. Yes, it's still the mean, it's still the average, but there's a whole bunch of variation in that data set. And you could basically have, instead of the ages of students at Central Washington University, you could have the ages of individuals from anywhere, right? And they could range anywhere from 0 to upwards as high as 100 or above. That's going to be a widely scattered data set that is scattered broadly around the mean. whereas the age of the Central Washington University students is going to be a much less scattered data set because there's not going to be that many students that are really drastically higher or lower than the mean. So in essence, high variance means that there's a lot of scatter, that there are a lot of varied values in the data set. Low variance means that there is less scatter. In other words, most of the measurements are closer to the mean. Okay? The formula for variance, again, this is S is to designate the variance, and it's S squared, and I'll explain why in a second. Okay? So if you look at the top, the numerator, we've got our summation again. And what we're doing here is we're taking each of the data points. That's where the X with the subtext of I, that I would range from, like, if we're looking at 100 examples, it would be 1 to 100. So X1, X2, X3, all of those. And from those values, we're subtracting the mean. So we have, again, the X that's representing the mean. So what we essentially do is we take every single value in our 100 student data set and we subtract out the mean and we see the difference. What that tells us is for each one of our data points, it tells us how much different the X value is than the mean. The issue with this is that sometimes the X values are going to be higher than the mean, which is fine. We subtract out the mean and we're going to have a positive value left over. But sometimes they're going to be negative. And if we don't correct for the negativity, when we combine them all together and do the summation, we're going to get somewhere pretty close to zero because they're going to cancel each other out. So what we have to do instead is we take the X sub I, which is all of the 100 instances of X, we subtract the mean and we square it, because when we square it, any negative value is going to turn into a positive squared value. That's how we get rid of the negatives. Okay? So we sum up all of the squared values of xi minus x, and we divide, instead of this time dividing by n, we divide by n minus 1. And there's a reason for that. That is a statistical reason. It has to do with the degrees of freedom, and I'm not going to go into it because it's not relevant for our needs right now. Just know that subtracting by n minus 1 instead of n gives us a more conservative, more cautious, and a safer estimation of what our variance is. So let's go through this again. Formula for variance: s squared, because we're squaring both sides. So in a sense, if we were to drop the s, the squared off of the s, and drop the squared off of the summation on the numerator, we're really looking at a similar value, but we have to do the squaring because we have to get rid of the negatives. So s squared, your variance, which is symbolized by s squared, is equal to the summation of x sub I minus x squared over n minus 1. And that will give you a single value that will account for all variance in your data set. It basically adds every bit of difference between the mean and each data point into one single number. Okay? So I already explained why it's squared, to get rid of the negative values. So here's a kind of a visual example. It's a very simplistic visual example, but it will show you a little bit about variance, and then we're going to get into something called standard deviation. In statistics, as you probably are aware, we don't talk a lot about variance, but variance is important to understand how it gets us to standard deviation. We talk much more about standard deviation. So in our instance, in the first column over on the left, we have our x values. These are x sub I, so x1, x2, x3, x4, x5, so on. And then in the second column, we have the mean. The mean in this particular instance is 8. Remember what we're going to do when we're creating we're calculating the variance, is we're going to subtract the mean, which is 8, from the x value, from each x value. And in the first instance, we get negative 2. In the second, we get negative 1. In the third, we get 0. Fourth, we get positive 1. And in the fifth, we get positive 2. You would see that if we added all those numbers up, we would wind up with 0 because they would cancel each other out. So that's why we have to square everything. So if we square the negative 2, we get 4. If we square the negative 1, we get 1, and so on. And it's really okay to do that because we're looking for absolute values. We're looking for distance from the mean. We don't care if it's positive distance or negative distance. It's still distance. So we do want them all to be in positive values. So we then sum all those up, and that gives us our variance. So our variance, in this case, symbolized by S, is equal to the summation of x minus the mean squared over n minus 1. Let's move on to standard deviation because that's really a much more useful tool. Variance is interesting to tell us how much scatter we have in our data set because it measures the amount of variance between each of the data points in the mean and sums it all up. But standard deviation is the kind of nomenclature that we use to indicate how much variance we have in a data set. So let's break it down. Deviation is the distance from the mean, and standard is a standard unit. It's a standard unit derived from the variance. And we measure standard deviation in units of deviation. So the simplest way to describe how we calculate standard deviation is we just take the square root of the variance. Remember, we had to square everything in the variance to get rid of the negatives. Well, that leaves us with a rather large number. So we just take the square root of that value, and that becomes our standard deviation. Each measurement accounts for some portion of the variance. So each one of those units, a standard deviation, you could have one standard deviation, two standard deviations, even up to 3 standard deviations, and it's going to account for some portion of the variance in that data set. The standard deviation is a translation of a measurement's variables into standard units. Standard deviations can be above the median, or they can be above the mean or below the mean. So you can have a positive standard deviation and a negative standard deviation. And standard deviations generally span from values of 0 to 3. It's possible to have higher. You have enough scatter in your data set that you have a standard deviation or a value that is more than 3 standard deviations away from the mean, but that's pretty rare. So here's the formula for standard deviation. So we use S again. S is our standard deviation. X.I is our current measurement. So it's the same. Basically, it's the same variable. Same equation that we use to calculate variance. So the summation of xi minus the mean squared divided by n minus 1, and we take the square root of that value, and that gives us our standard deviation. So again, I didn't talk too much about why we use n minus 1, but we use n minus 1 to get what's called an unbiased estimator for the variance. It's just a more conservative way. If we have 100 students and we're looking at ages, the distribution of ages for those 100 students, if you divide by 100, your variance in this particular equation is going to be a little bit lower because you're dividing by a larger number. So if you divide by 99 instead of 100, and there's a statistical reason why we do that I'm again not going to go into, it'll give you a slightly larger variance, and that way you can be sure that your variance and your standard deviation are more accurate, are more likely to capture the true variable, the true value in the population. Let's talk about sample versus population. So the whole kind of idea of statistics, and we'll get into this when we talk about inferential statistics, is we want to look at a sample that represents a population. Now, if we're going to look at all students in Central Washington University, that's about 12,000 students. That's a lot of people. And I'm not going to go to them and ask each one of them for their age because, one, they may not want to give it to me. It's not feasible. It's going to take me way more time than it's worth to ask every single student what their age is. So what I'll do is I'll pull a sample of students, and the sample will represent my population. Now, the way you select the sample is pretty key. It's pretty important because your sample needs to be representative of your population. If you select only graduate students in your sample, it's probably not going to be representative of the population because the sample is going to be biased towards older age students. So you want to make sure that your sample represents your population, and the way you do that is just to ensure that every member of the population has an equal chance of becoming a member of the sample. So quite often in statistics, we want to know something about a population, and often these populations are really large. For example, all U.S. citizens over 50 would be a really large sample. We can't possibly talk to every U.S. citizen over 50. So we draw a smaller sample. We learn what we can about the sample, and then we apply the results to the overall population. And that's a process called generalization. We conduct our statistics, we conduct our research on our sample, and then we generalize those results to the larger population. And basically what we're doing is we're inferring that what we learned about the sample applies to the larger population. Now, that works out pretty well if things are set up correctly, but there's a lot of ways that can go wrong. And we'll talk about that in the inferential presentation or session that will follow this one. So like I said, selecting the sample is very important. It should represent the population in many ways. If our sample is too small, we can't accurately generalize our findings to the population because we didn't get enough of a sample. We can't track enough of the variability. We can't track enough of the features of the sample to actually say that this is going to apply to the population. If the sample is too large, well, we've made our life too hard. It's going to be more difficult than it needs to be. So if our sample does not represent our population, for example, all members of our sample are under 55, but we wanted our sample to represent the population of people who are over 50, that's not representative. It's not going to work. So what we do is what we learn from the sample won't be generalizable to all the members of our population who are all adults over 50. So we got to make sure that the sample, the attributes and characteristics of our sample are the same as our population. So here's some notation, and this might be important as we get into JASP and start looking at some of these. The notation is fairly standardized. For example, the sample mean we already talked about is X bar, and that is a mean for the sample, and it's a standard nomenclature that we use when we're looking at sample means. But for the population, because there will be a mean for the population as well, that is a Greek character called mu. And that is what we use to indicate what the population would be in the sample. Now, what the mean would be in the population. Now, if we've done a good job of selecting a sample and we've calculated what the mean of a variable is in that sample, then ideally the sample mean will be very close to the population mean, right? All right, we're looking at variance for the sample. The variance is noted as S squared. And for the population, we use another Greek letter, but we also indicate that it is squared. And it's the same value with standard deviation. We just drop the square. So I'm going to talk a little bit more about why we use n-1 in both the variance and the standard deviation. So we use n-1 as the denominator for the sample. And the reason why we do that is, I already talked a little bit about this, but at least you'll have it on a slide. Dividing by n-1 as opposed to n will give us a larger variance and a larger standard deviation, because remember, the standard deviation is derived from the variance. There's an example, dividing 10 by 5 equals 2 and dividing 10 by 4 equals 2.5. So you see that you get a slightly larger variance. That way the variance and standard deviation for the sample is more likely to contain the variance and standard deviation for the population, right? So we're being extra careful here. By dividing by n-1, we'll come up with a slightly larger variance and a slightly larger standard deviation in our sample. Then when we generalize back to the population, we can have higher confidence that we've actually captured both the variance and standard deviation in the population. So we're just being more conservative in our measurements, and we call this an unbiased estimator. Now back to standard deviation. So if variance is the average amount of a sample variance squared, so that's the summation of the distance of each data point and the mean squared, and standard deviation is the square root of that value, then let's see, what am I doing here? What does that mean? The values of variance and standard deviation are 100% controlled by the amount that the measurements differ from the mean. We've kind of gone over that. We've kind of gone through that. So if you have high variation, you'll have high variance and higher standard deviation. And if you have low variation, you'll have low variance and standard deviation. So we might say that a variable has a mean of 100 and a standard deviation of 5. Is that a high standard deviation or a low standard deviation? It's fairly relative. But if we look at another example, say that a variable has a mean of 100 and a standard deviation of 15, that indicates to us that we have two samples. The one with a standard deviation of 5 has far less scatter away from the mean for each of the 100 data points. So it just means that the data points themselves all have values that are closer to the mean than the second example, which with a standard deviation of 15, that means that there's more scatter, there's more distribution, and there's more distance for many of the data points from the mean. One caution around this is outliers. If we run into a situation, for example, in our second example, we may run into a situation where we have 2 or 3 very high outliers. That means these are data points that are very far from the mean, and they throw everything off. So that could be the case, but most likely what this is indicating is in your second example, you just have more distribution. It's a broader distribution. Here's how we can see that visually. In the blue line, we have a tall and narrow bell-shaped curve, and this one is thin indicating that the data points that make up that sort of distribution are pretty close, are closer to the mean. And the mean is where the zero data or the 0 point there. That's not to indicate that it's the zero value. That is standard deviation units at the bottom. So the mean would be no standard deviations away from the mean. That makes sense. And then you see both on either side of it, one standard deviation. Those to the left are negative. Those to the right are positive. 1, 2, and 3 standard deviations. 3 standard deviations on both sides of the mean generally will account for almost all of the data points in any distribution. The orange line is shorter and it's wider. So it's indicating that there's more distance of the data points from the mean, and there's more scatter across the 3 standard deviations on either side. A little bit more about standard deviation. It is specific to a data set. It is derived from the values of that data set, and it's typically measured in units. Standard deviations are measured in units. So 1 standard deviation away from your mean is going to give you typically 34.1% of all data points will be contained in that 1 standard deviation. In this particular case, we can look at there's 1 standard deviation to the right of the mean, and it is going to be 34.1% of all of the data points in your data set. It works the other way on the other side. 1 standard deviation away from the mean to the left also accounts for 34.1% of your data points. So typically in a data set, 1 standard deviation, either positive or negative, is going to account for 68.2% of the data points in your data set. Now, why does that always work out to be 34.1? Well, remember, your standard deviation is going to be completely dependent on the scatter and the distribution of your data points. So if you have a broad distribution, if you have a wide scatter of your data points, that section that makes up 34.1% would be far broader, far wider than what it's showing in this particular visual. If you have a very tight data set, very low scatter, then that's going to be much more narrow. But it would still account for 34.1% of the data points. It's just the shape of the bell-shaped curve would change. So 2 standard deviations in either direction typically represents about 47.7% of the data points, either positive or negative. And if you put them together, then within 2 standard deviations, you're going to have 95.4% of your data points. So almost all your data points are no more than 2 standard deviations away from the mean. This is important because it allows us to see those data points that might be outliers. If we have 2 or 3 data points that are very, very far away from the mean, they're going to impact the way that this data is distributed. They're going to impact the standard deviation, they'll impact the variance, they'll impact the mean, but we'll be able to see it a little better. If you go out 3 standard deviations, I don't know the exact values, but I think it's like 99-point-something% of your data points fall within 3 standard deviations, either positive or negative from the mean. So back to mean. We talked about this already, factors that it can impact the accuracy of the mean. Not so much the accuracy, but more of how a sample mean represents the population mean. So these are things that can make it so that if you've drawn a sample of 100 students from Central Washington University and you're calculating the average age of that 100 students, here's how things could go wrong. And we already talked a little bit about if your sample size is too small, it can't truly be representative of the population. So that's where things can go wrong. And I've seen studies where sample size was ridiculously small, and it really does compromise the generalizability of the results back to the population. You could also run into a situation where your sample is not representative of the population. Just like the example that I talked about with using the average age of graduate students to represent the average age of all students at Central, that would not be a representative sample. And then I've talked about outliers. These are extreme values that impact the mean. And those extreme values that impact the mean can also impact the variance and the standard deviation. Now I'll give you an example. Here's an example of an outlier. These are house prices. There's Ellensburg, Kittitas, Sealy, Yakima, Kittitas, Ellensburg, Kittitas, and Yakima. And if you look at all of the different house prices, they seem to all fall within a particular range. So if you were to calculate the range, except for one, if you were to calculate the range of the first 8, you come up with a mean of $307,064. But by throwing in that ninth house would be an outlier because it would be far from the mean otherwise. It brings the price up to, I'm sorry, I've got them backwards. The mean with the outlier is $392,200, and the mean without the outlier is $291,250. And you see what your standard deviation is. Your standard deviation is huge when you include the outlier. Your standard deviation is only 53,769 when you don't include the outlier. So you see the impact that the outlier has. It has an impact on the mean. It draws the mean up by $100,000 across the other 8 houses. And it also impacts the standard deviation because it's accounting for so much variance and subsequently a broader standard deviation because it's really throwing things off. So when you have outliers like this, you just have to be aware of them, but you also might want to think about potentially, if you can, eliminating the outliers, or there are other tools that you can use to actually reflect the data set without having to use the mean that's impacted by outliers. And that is median and mode. Median is probably the most common. So what if you can't or shouldn't use the mean because you have outliers in it? Then use the median. The median will tell you good information that is valuable. It's not the same as the mean. The median is the middle value. If you were to take all the values and you were to sort them in order and line them up, you find the one in the middle and you say, boom, that is the median. In that case, 50% of your values are going to be higher than the median and 50% will be lower. That's not always the case in the mean because remember, outliers can draw the mean in a direction that is biased. But in the median, it's always 50% or higher and 50% or lower. And in some cases, it can be quite different than the mean, especially in the case where you have outliers. It's best for continuous data when you're looking at numerical values that could be in any range. And quite often in the news and the media, you'll hear the median house price. And there's a reason why they do median house price because 99% of the houses in a particular area fall within a certain range. But there's that 1% that are way out, way higher that would draw your mean just too far over and give you too much variance and a huge standard deviation. So we use median instead. Mode is another measure, and this one is best when we're using categorical data. So, if you were to say that we're going to measure kind of the number of quarters that students spend at Central Washington University to earn their degrees, what we would do is we would have a series of numbers that would range from 1 to however many the most student ever took, or whatever's in our sample. And it could be 1 to, say, 20 or 1 to 25 or something like that, quarters that a student took to earn their degree. Those are all categories. So you're not going to have like 1.1 or 1. Typically you wouldn't. You can have 1 quarter, 2 quarters, 3 quarters, 4 quarters. And you'll have a measure for 100 students. You'll have a measure of the number of quarters it took for them to complete their degree. The mode would be the most common measure. So let's assume that we have a big chunk of that 100 students. Maybe it's 30, and they all finished in 16 quarters or 12 quarters or whatever the number is. Then you would have a mode. You could also have multi-modes or multimodal data, which means that you might have 30 students that finished in 16 quarters and another 30 students that finished in 20 quarters. So you would have 2 modes, and you would call that a multimodal data set. Here's an example of median and mode. You can look at this kind of on your own, but you can calculate the mean. The mean of this data set is 6.625. The median is 6.5. So in this case, the median and mean are pretty close. Now, why do we have 6.5? Why is the median 6.5 when it's just supposed to be the middle? Well, in an instance where you have an even number of entries, and when you get to the middle, there's no real middle. There's no odd number that says I'm the one in the middle. There's 2 in the middle, and they're not the same. So what you do is you average those. In this particular case, we had a 6 and we had a 7 that would make up the middle. Because we have an even number of data points, and we just averaged those and got to 6.5. So our median in this is actually 6.5. Our mode, the most common occurrence, is 5. It happens the most times. It's not multimodal. It's just 5. So median, mean, median, and mode are often referred to as measures of central tendency. The last thing we're going to talk about is range. Range is the spread of values of measurements in a data set. So let's think about our example of 100 Central Washington University students, and we're looking at their age. There's going to be a lowest value, and there's going to be a highest value. And that is the range of the data set. Quite simple. So if somebody is, maybe a prodigy and they're coming into Central Washington University at age 16, and somebody has gone to college later in life and they're finishing up at age 45, that could be the range in our sample. So lowest value to highest value is the range. And what you basically do is you take the highest value, you subtract the lowest value, and you come up with your range. In this particular case, 45 minus 16 is 29. So the range in my data set, my example that I gave you, is 29. Sometimes the range is divided into quartiles. We'll look at the bottom 25%, then we look at the quartile that runs from 26 to 50, then the quartile from 51 to 75, and then the quartile that runs from 76 to 100. The range of data points is probably going to fall mostly between 25 and 75 in the middle two quartiles, and so we call that the interquartile range because it accounts for the largest number of data points. The range is not really used that much. It's not used as much as mean, standard deviation, or variance, but it's good to know what it is because it tells you kind of the overall variation, the amount of, if your range is fairly small, then you know your 100 data points are very close to each other. If your range is very large, then you know you've got a pretty broad spread. But it's good to know what it represents. And that's the end of this first presentation. Go ahead and look at this as many times as you choose. Let your instructor know if you have any questions about any of this, and stay tuned for the next presentation, which will be on inferential statistics.